Hey everyone, Mr. Tima here. Welcome back. We're going to do part 6.3, electricity and magnetism, really talking about the electronical circuit components of all of this. And we're going to be building some, we're going to be doing some simulation buildings, we're going to be doing some snap circuits. So you're going to get a lot of circuits thrown at you, but there is a little bit of math involved, some general math that I want to make sure that you understand. We're not going to go as hardcore into it, but we are going to get the basics covered. Okay. And by this point, we should be knowing a lot of these terms like cell and voltage and current and everything like that. All right. There are two major types of circuits. I mean, there's always a simple circuit, which is usually a series circuit, but we're really talking about two major ones. And there is a series circuit and there is a parallel circuit. The first is a series, okay? A series circuit, and I'm just going to put all this out here so we can talk about it, but a series circuit is where the current can only travel through what we call a single path. Again, remember, which way does the current flow? The current comes from the positive and it goes around to the negative. All right. So remember, the electrons come out the negative side, but the current flows positive to negative. So we kind of get this kind of flow going on this way. All right. Now we have three resistors here. You have to, on this river, if you will, if we go back to the water analogy, you have to go through each one of these resistors. All right. You have to jump each one of these. All right. So we say that the current can only travel through a single path. If there was a break in the river, if one of these resistors would pop, because a resistor could be a light bulb, right? Then the whole thing's going to go out because the river would basically be dammed up and stop moving. Everything in the river is going to have the same brightness, so every light would have the same brightness, and each device receives a fraction of the total push because as you push through this one, you're going to lose a little push. You're going to push through this one, you're going to lose a little push through this one, and then there's going to be a large draw on that, and you're going to need to be a big push of energy to keep that going. So a series circuit, one way through. This is kind of a picture of our series, right? Again, here's our schematical drawing, and here's what it would look like. You have to go through both resistors. This is what old school Christmas lights used to do, okay? Sorry, I'm going to hide that. Oh, goodness, of course. Hang on. Back to it. There we go. All right, but here's how old school Christmas lights work. If one of these lights broke, the whole strand went out, and you'd have to find each light bulb and all that kind of stuff. Again, schematical drawing versus actual drawing. Okay, and now if you look at it, you've got ones with multiple strands on there, and sometimes you'll see like just a third of the strand go out or half the strand go out, and that's something called a parallel circuit. So a parallel circuit is a little different. Just going to put all this up here so we can talk about it. But a parallel circuit, now look, positive right up here. Now you have a choice here. You can either go through this resistor or you could continue on to this resistor. And then you could go through this resistor or you could come up here and go through this resistor. But eventually, no matter which resistor you go through, you eventually kind of join back on to another branch of the river, and then you have to all bat up and come back together. So no matter where you go, you're going to meet back up, but you have some choices here. So if one of these breaks, you could go through the other two. There's still another road or another path or another river joint to go through. Just like humans, current takes the path of least resistance. So if these resistors aren't equal, let's just say they're not equal. Let's say this is a really weak resistor and this is a really strong resistor. There'll be a lot more flow through this weaker one than there will this strong one. Okay, and you're going to see that in one of your simulations you would do. All right. The bigger light would be dimmer in a way. So if this was a bigger light, like a 120 volt light versus a 10 volt light, you'd have more flowing through the 10 volt than you would the 120 volt. Okay. And then each would receive the same push because look, they all are connected to this side of the river and each are going to get a push. And it might take longer to get over the little rapid, but at the end of the day, they're all going to come back together. All right. So parallel circuits. All right. So look, as it comes here, you have a choice. You can either go this way or you can go this way. But at the end of the day, after you go through there, and it might take you more time to get through one than the other, but at the end of the day, you're going to join back up as a happy little family and you're going to continue on your journey. All right. So that's a parallel circuit. So your house is a combination of parallel circuits. Okay. We don't hook up your house in a series, because that means if the coffee pot blows something up in the kitchen, like it blows a fuse, that means the whole house would go out. That doesn't happen very much. Okay, now some of you are saying, well, wait a minute, if I plug into this outlet in my wall and I got a hair dryer going and the fan going and whatever, that it might blow your room out, as in like your room power turns off, but the whole house room power doesn't turn off. Okay. Too many devices can cause the wires to overheat, produce too much. There's too much current flowing. So there are some safety features in place. The first is a fuse, all right? Now, a lot of you may have heard of something called a fuse box in your house. You don't have fuse boxes in your house. Well, maybe if you have a really old house, and by old, I mean like way back, built in like the 30s and 40s. A lot of you don't even have these. Fuses literally were a tube. They were like a long tube, and they had like, you literally could look in there and there was a piece of metal in there. And when it got too hot, there was too much current flowing per second, that metal would actually melt and it would stop. And then you'd have to pull out the whole tube and you have to put a whole new tube back in. That's not what you have. You have something called a circuit breaker, which a circuit breaker is like, you've seen the like little panel and it has the little black switches and stuff. That switch, inside that switch has a wire, okay? And that wire, when it gets hot, gets really loosey goosey. And when it gets loosey goosey, when it gets that warm, it kind of gets really flimsy and it allows the switch to flip, turning it off. And then you go back downstairs and you flip the switch after you've unplugged it or whatever, and it turns back on. Again, if it's too much, it'll flip right back off. Okay. And eventually these wires wear out and you have to replace the breakers as well, but it's a different thing. Okay? Complex. Complex is actually what's going on in your house. All right? Where let's just say this was your bedroom again, that you blew the fuse. Maybe this is the hair dryer and this is the fan, but this is the hallway. Okay, so it splits off in the hallway, electricity still stays on, but you could actually blow this up and turn that off. These two would stop moving and this one would keep going. All right. Notice this right here, these two together, these two right here, this is a series. But when you combine all three of these, that would be a parallel. This guy is in parallel with these guys. Okay. All right. We'll real quick check of understanding. And as we move through the rest of these notes, you're going to have to pause the video, and we're going to pause the video and have you take some guesses and then restart the video. And really, again, nobody's going to know if you do this, but it's a good challenge to see if you know what you're talking about. So the first thing we're going to talk about is omega. And omega is, who remembers, is, oh, I don't want to push that. Want to push is the resistance, right? Omega is the symbol for resistance. So I want you to rank these A, B, C, and D. You just need to put the letters. Which one of these guys has the highest resistance to the lowest resistance? So again, if you think A has the highest resistance, you're going to write A, and then like let's say you have D as the lowest resistance, so you might put A, B, C, D. Okay, so I want you to rank them from highest resistance to lowest resistance. So go ahead and pause the video and try to do that right now. Try to take a guess. All right, we're back. So hopefully you did that, and I'm going to tell you right now the answers are B has the highest resistance. Then it goes C. Then it goes A. And then finally it's D. Now, why? Why would it be like that? Well, look, B has to go. You have to go through two resistors. Have to. That's why it's the most. None of these other ones, you have to go through two resistors. All right. And then D, actually, you're thinking, well, wait a minute. D, I have to go through one. I have to go through one, but over here I only have to go through one. This is where it gets a little confusing, and we're going to talk about it later on in the notes. But even though you have to go through one, you only have to go through a fraction of one of them, okay? Because since you're able to split, you have that choice that actually lessens resistance as well, all right? So this has the most, this has the least. Again, look, A, you only have to go through one. C, you have the choice. C is the second highest resistance because you may have to go through two, you may have to go through one, okay? All right, let's try it with current now. Let's try it with current, or C. Let's try it with current. And who remembers, what do we measure that in? That's I, right? Okay, current is I. It's measured in amps. So which one of these guys has the highest current and which one of these guys has the lowest current? Pause that video and we'll come right back. All right, we're back, and the answer is D has the highest and B has the lowest. And then C would be the second lowest and A would be the second highest. And if you actually think about it for a second, if you have the highest resistance, or excuse me, if you have the lowest resistance, then you're going to have the highest current flow through it. If you have the highest resistance, you're going to have the lowest current flowing through it. And again, vice versa with the C and the A. So these are actually inverses of each other. They're inverses, indirect relations. They're inverses. I'm going to put inver. They're inverses, okay? They're inverses of each other. All right, and then finally, let's just talk really quickly about voltage. Again, voltage, all right? What is the voltage? Okay, so from the highest voltage to the lowest voltage. All right, pause the video, come right back. All right, you're back, and then again, the answer is B, C, let's see, it's a little small there. A, oh goodness, my little clicker writing is all over the place right now. And D. They're actually the same as the resistance. And why is that? Well, if I have the highest resistance, which has the lowest flow, I'm going to need the biggest push to keep it moving. Okay? If I have the lowest push, that means I probably have the lowest resistance, which means my current's flowing pretty good already. Okay, we're going to keep talking about these as we go through, but hopefully that helps you see that. All right, so there is this term of EMF and potential difference, PD. Okay, and that all has to do with the push. Okay, so if the EMF of a battery is 9 volts, and remember, what does that mean? What does that mean? That means for every one charge, we're going to have to use how many joules of energy? And that's 9 joules. We basically need to use 9 joules of energy for every one charge that we want to push through that battery. And it has a charge of 2 coulombs, all right? So what would be that flow? Excuse me. All right, well, so instead of one charge, we're trying to push 2 charges. So for every charge is 9 joules. So for every 2 charges, it's not going to be 9 joules. It's going to be 18 joules. Pretty easy. What is the PD across the resistor? That's 24 joules of heat produced of a current of 2 amps for 10 seconds. Again, 2 amps means that for 2 amps means we have a flow of 2 coulombs per second. So it's flowing for the door, or the flow of it has been 10 seconds. So we know that we have 20 joules. Okay, we have 20 joules kind of going on here, or 20 coulomb charge, excuse me, 20 coulombs of charge flowing. All right, so how do we do that? Well, we take how many we have, 24, we have this many joules of heat produced over this many joules that's going on, so we know that it was that much of voltage pushed through. All right, and we'll work on those. Power, real quick, power is voltage times the current. Okay, if a 2 amp flows through a resistor with a PD of 4 volts, how much power is dissipated? Remember, this is I, this is V, P equals IV. Bang, bang, we know that that's 8 watts. That means that an 8-watt light bulb would require a push of 4 volts at a current of 2 amps, okay? What will the power be dissipated of a 4 amp, that's I, that flows through a resistor of 55 ohms? Now that's R. Well, wait a minute. We don't have V. Well, but remember, we know from Ohm's law that V equals IR. Okay, so we can actually figure out that V. Okay, so we know that V is actually 220 volts by doing this math. Now we have V, we have I from up here. That I didn't change. We multiply it and we see that that's 880 watts. So you can either memorize all these things to calculate power. You can memorize all these formulas up here. Or as long as you know that power equals VI, and you know V equals IR, you can substitute and always kind of find these. And that's what this is walking you through. It's just substituting V equals IR to figure out. Instead of memorizing 3 equations, you only need to remember that P equals VI. All right? So we go to an electrical motor. This is kind of where you pay for money and all this kind of stuff. So an electrical motor uses a 10 kilogram, lifts 10 kilograms in 3 meters, and it took 5 seconds. Okay, what is the PD across with a 12-volt motor? How much current flows? So we're looking for I. Okay, we're looking for I. We have V, but we have this thing up here. Well, what is this? This is mass. Okay, this is a distance, a displacement, if you will, and this is time. How are we going to solve this? It's actually not that hard. You just have to remember that you have to think about things that we've talked about in previous chapters. We can figure out the work done or the energy used because we know potential energy, something being lifted. We know mgh, m, which is 10, g, which is 10, and h, which is 3. So if you do that, bang, bang, we get 300 joules of energy. We know that the total energy here is 300 joules. Remember, power is work done over time. It's a rate. Well, the work done is this energy, 300 divided by the time, which is 5 seconds. So we know that the P is 60 watts. Well, it's real simple then. Now we go back to our equation of P equals VI, or if we're looking for current, we can solve for I. So that's just P divided by V. So we take our P, which is now 60, divided by 12, and we get the answer that we need a 5 amp motor. This is what people have to do when they're buying stuff at the store. You go to Home Depot, go to anywhere that you need to buy an actual motor, see how much strain you're going to put on your engines and stuff. This is important. If you want to be in engineering, this is kind of how it works. All right, so combinations of these. How do we do the math? Here we go. Okay, we already talked about that. Good to go. Basically, there's this equivalent resistance. This is important. REQ, the equivalent or the total, the magnitude of the resistance. In a series circuit, it's really simple. We just add up the resistors, okay? So in a parallel circuit, we have 1 over the total resistance is equal to 1 over plus, 1 over plus, 1 over plus. We'll show you examples right here. First of all, the first thing you need to do is this series or parallel? It's a series, okay? And since it's a series, we're literally just going to add the resistors together, okay? And we get 21, no biggie. Is this a series or a parallel? It's a parallel. Since it's a parallel, it's 1 over 8 plus 1 over 12. Okay, so wait a minute. That's one. We have to use common denominators here. So we have to use 24 as our common denominator. Okay, well, this then becomes what? This becomes 3 over 24. This becomes 2 over 24. If we add these together, this becomes 5 over 24. But remember, that's not the answer because it's really 5 over 24 equals 1 over REQ. So when you do this right, you can cross multiply and divide, or we just think we can do the reciprocal. You get your answer and take the reciprocal. So it's 24 divided by 5, and your answer is 4.8. Okay, I can walk you through that in class if you need more help. Let's try another one. Here again, when you have a big complex circuit like this, notice what we have to do is we have to simplify it to a much more manageable circuit. So this little section right here is just a series. This here is a series, so we're going to combine them and make it 9. This inside this entire parallel is a little series up here. So we combine these two and make it an 8. Now we look at it and say, okay, this is all by itself. But this guy right here is a parallel right here, right? So we do the 1 over REQ, and we can simplify it to this right here. Okay, now all of these are a series together. So now we can combine it and get our simple answer, okay? Not so simple? Let's try this. Okay, now look. What is this? this is a parallel right here. This is a parallel. But this guy is out here on its own. But when we combine these and get our new answer, it will be in series. It'll be in series with this guy. So we do this right over here. 1 over 5 plus 1 over 5 is, who's got this? 1 over 5 plus 1 over 5 is 2 over 5. Take the reciprocal. This entire thing over here is really 2.5. 2.5 plus 4 is 6.5. Try this one real quick. Take a second, see if you can do it. All right, this right here is a series that's within a giant parallel circuit. All right, so we do the series first and we get 9. We simplify. This is 9 ohms right here, this top part. 9 ohms, okay? But now 9 ohms is with this 3 ohms. So this is 1 over 9. This is 1 over 3, but we got to get to a common denominator, right? So it's really like 3 over 9. Okay, 3 over 9. We went from 1 over 3 to 3 over 9. And why did we do that? Because this is 1 over 9. It's really 4 over 9 because we added them together. Then we take the reciprocal. And 9 divided by 4 is 2.25. Here we go. Give this a shot, and then we'll come back in 2 seconds. Pause that video. All right, we're back again. So again, we got like a little series in with a parallel, and then once we get this answer, we can do another little series over here. So again, I'm going to go series here. This is 15. This guy's 15 ohms over here. All right, we got this 5 down here. So we think about it as like 1 over 15, 1 over 5, which really becomes 3 over 5. Okay, becomes 3 over 5. We add it up here to this 1 over 5. This whole thing over here is 4 over 15. Take the reciprocal. That sucker really is 15 over 4. So if we do that, we divide 15 by 4. Okay, and then we're going to add it to the 6. So it really, like this 15 over 4 becomes 3.75. Sorry, that cut out right there. And then we add it to our 6 to get 9.75. I know that some of you are confused. Again, we're going to have to go back over this during class. All right, here's a cheat sheet, great slide for you. Kind of has everything written out that you need to know. You might want to take a screenshot of that, but there you go. Kirchhoff's rule, real simple. Kirchhoff says, hey, the current that split in a parallel circuit is going to come back together and join together at the end. And we kind of already talked about that in a parallel circuit. All right, super fast. I know these notes have been going on a little bit if you missed, but there are things that we can use to measure against things, and this is called a voltmeter. A voltmeter measures across a resistor. It has an infinitely high resistance. Why would a voltmeter have an infinitely high resistance? And the answer is, if it didn't have a super high R, if the voltmeter didn't have an unbelievably high R, then some of the current would flow in this and be like a parallel circuit. We don't want that. We just want to measure. We don't want to interfere with what's going on here. An amp meter, on the other hand, is in the circuit. And the reason that an amp meter is in a circuit is because what do amps measure? Amps measure the flow. So if we want to measure the flow of something, it has an infinitely low resistance. And the reason that it has an infinitely low resistance is we want it to be part of the circuit. We want to measure how much is flowing through here, but we don't want to interrupt that flow and change the flow. All right. Again, with IB, sometimes these look like the same pictures, but they're not. They're not the same pictures because look, this guy has a switch in here. So these are actually the same circuits. It's just this guy doesn't have a switch and this guy does, but everything else would be measured exactly the same. All right, real quick, I'll try to make this really fast. Sensors. What's really cool about these sensors are things that you've never thought about. So a thermistor, which we've not talked about yet, but a thermistor, this is the symbol right here, that's how fire alarms work. If you look at this, we want the current to flow through here. Everything's fine. Everything's fine. As soon as the temperature goes up, this piece of metal, this piece of metal has broken the circuit. There's nothing flowing in here. When the temperature gets really hot in your house, if it senses a fire, it has to be a drastic change. Sometimes, if you look up at the ceiling, the ones that have the sprinkler system, this is a little red capsule. When that capsule breaks, the resistance goes way down, which allows this to connect the circuit. And when it connects the circuit, that allows electricity to flow through and the alarm is sounded. The alarm's kind of always ready to be on until it's like ready to go. And when that connection happens and electricity flows through it, bam, now we have a fire alarm. Same thing with a light sensor. What a light sensor does is it's right there. When the sun hits it, this becomes really hot, and there's all those little particles like in the resistivity. The sun actually causes a really high resistance. And when there's a really high resistance in this light or LED sensor, what happens is the electricity can't flow through. So the light doesn't come on. Your solar light doesn't come on. At night, when the sun goes away, these little dots disappear. All of this happens. The dots disappear. There's no resistance. The current's allowed to flow through, and bang, your lights come on. Same with an automatic light switch, same idea. All right, last one I want to talk to you is a strain gauge. Where have you seen a strain gauge? Where would you think that there's a little kind of things of wire, and then all of a sudden, when weight is put on it, these wires compress a little bit, which again makes the cross-sectional area go down. And when that cross-sectional area goes down, it stops the current. It stops the current, which maybe sends off an alarm or something or notifies somebody. Some of you might be thinking about drive-throughs. When you pull up to a drive-through, your car goes on top of this. And when your car wheels sit on top of here, it pushes down, and guess what happens? They get notified inside that there's something with enough mass on there that there's a car sitting there ready to have their order taken. Okay, this used to be how stoplights worked. Like if you ever get to a turn lane, like on Sawmill Road or something, like this might be the straight lane here, but all of a sudden here's the turn lane. You may notice that in that turn lane, there's like a little box cut out. That little box cut out is where your car has to sit. There has to be enough cars sitting there so that the light will give you that green arrow. That's how it knows. Now we use cameras, but that's kind of how it was. And there's actually one other area for safety that a strain gauge happens, and that happens on bridges and overpasses. You don't even know this, but on bridges and overpasses, those little wires are right here. Everything sags eventually. If we get to a point where the bridge sags too much, again, the same thing happens. It's sagging too much. The alarm goes off. People know, engineers know, to get out there and start fixing that bridge. Guys and gals, I know that was a little bit long notes. We'll be doing them in class together. This was to serve in case you needed more help or needed more clarification or practice. Again, reach out. I know those calculations can be a little tough sometimes. And again, until next time, Mr. Tima is out of here.